online. The slide should also be online already right now. So has anybody seen the egg drop problem beforehand? Okay, you've just lost your voice. I'm so sorry to hear that. Actually, I guess I'm not hearing it because you've lost your voice and you can't say that. Exactly, exactly. Right. So if you've seen it, if it's something you haven't seen, you can speak up. But if it's something you've seen before, please don't speak up. Give people, a chance to have some fun. Okay. So what I want to do today is talk about egg drop mathematics. I am not really advocating for going outside and dropping eggs, watermelons, stuff like that. I really don't care about dropping objects. I care about using this as a springboard to talk about good math, to see good math, to talk about how do you attack problems. So see if I can make things a little bit larger. That's all right. Hopefully this is large enough and people can see. If not, grab a smartphone and I'll connect you to the Zoom room. So the way it works is the following. We have a building with n floors because we're mathematicians, and of course it has n floors. We have two special eggs, which my kids will kindly eat later tonight. Right? These you cannot find in most supermarkets. Fortunately, Williamstown has a phenomenal Stop and Shop, and I hope they remember that I'm saying this publicly. Wonderful Stop and Shop in Williamstown, where we sell these great eggs that have this remarkable property with this building. There is some floor that if you drop it from that floor or higher, the egg will crack immediately and be unusable. And as long as you drop it from any floor below that, no matter how many times you drop it, there is no damage to the egg. You could drop it 1 billion times if you want from a floor lower than that critical one, and there will be no damage. But as soon as you drop it from the critical floor or higher, it will break. And your goal is to find in as few drops as you can what n is. What is that critical floor where it will first break? And so before we started, I was actually talking to some of the people here about what have you done recently in the program. And I was told that one of the talks you heard recently was about notions of small, that there can be different metrics for small. So when I'm giving you the problem, and I know this might be a couple of slides later, when I give you the problem in as fewest floors possible, how do you interpret that? And you feel free to roll your eyes and go as few floors as possible. Elaborate on that as much as possible. What are you trying to do? Yes.
If you plot if you write the number of drops you need as a function of n, what is as a function f of n, then what is f asymptotic?
Well, because what is, can you come up with a formula so that if I tell you how many floors, you can tell me how many drops? But what do you think fewest drops means?
Probably because sometimes you'll be more lucky than others, like the worst case.
Good.
Some algorithm, and when you say few, you want to say worst case scenario, I still need just this many drops.
So who would like $100,000 today? Yeah, I was going to say, okay, you raised your hand first, okay? So congratulations. Now, unfortunately, the other side is you die. Okay. So he raised his hand. He volunteered, correct? So we've got some lightning strikes outside. Who brought the metal pole? So we're going to flip this coin. Heads, you get $100,000. Tails, you die. Okay, are you ready?
No.
No. Okay. What if we flip the coin twice? And if it's double tails both times, you die.
No.
What if we flip it 10,000 times? And if it's always tails, you die. And it's a fair coin. 10,000 times.
Maybe.
So should his answer be maybe if we're doing it 10,000 times? Can somebody tell me quickly? Oh, this is really large. Well, actually, maybe we should probably have it really large because this is life. 2 to the 10,000. Does anybody know how to quickly calculate that?
I don't know how to quickly calculate it, but I know the chance he goes outside right now and gets struck by lightning and dies is higher than you flip a coin and whatever you do to him afterwards.
Does anybody know what 2 to the 10 is? Around 1,000, right? So this is basically 1 over 10 to the 3,000. To put things in perspective, anybody know roughly how many objects there are in the universe?
Like 10 to the 80, yeah.
10 to the, let's round up to 10 to the 100, we're among friends, okay? 10 to the 100. So if you had a universe of universes, how much would that be? 10 to the 200. So if I'm thinking of a specific particle in a universe of universes, you've got to be thinking of the same specific particle as me, and that's only going to happen once every 10 to the 200 times. This is on the order of 10 to the 3,000. Would you be willing to risk it? Yes, for this one, absolutely. You would be willing to. No, I'm sorry. He raised his hand first. You don't get to risk it.
I'm just asking, would this be similar to the probability that you suddenly your heart freezes over?
That my heart freezes over, I start rooting for the New York Yankees, and that everybody here decides to become an English major and forsake mathematics. Yeah, the probability here is so small, I'm not worrying about something that's this unlikely. So the question was, what do we mean by in the fewest moves possible? Do you want to protect yourself from the worst case? What if the worst case happens very rarely? Would you be willing to have a better average time of how many drops you need, but occasionally it's really bad? Or are you very concerned and you just want to make sure that it's never, ever bad? It's a matter of personal preference.
I think that, I think that both of those are interesting problems that you could solve and I think could give,
Absolutely.
good results. So I think that it's best to just, because of some of this theoretical world, just to go both ways.
So one thing is to go both ways, but I was told I have 51 minutes. Yeah. So because I have 51 minutes, I can make homework. And so I hope that many of you, as people have done in previous years, will reach out to me and talk to me. So my email on the first slide, sjm1@williams.edu. If you can't figure out how to find my email, the program has more than enough people that can put in your place. Right? This is the 21st century. You should be able to figure out how to reach me. But if not, talk to some of the people here. We'll do one way. We will analyze the worst case scenario just because that's easy to do, but absolutely should look at some of these other things. So we want to figure out how to do this in as few drops as possible. We're going to interpret that as minimizing the worst case. You could also minimize the average case. Depending on how the floor is chosen where the egg breaks for the first time, your strategy could be very different. Maybe every floor is equally likely to be chosen, or maybe the higher floors are more likely to be chosen than the lower. Or maybe floor N is always going to have a greater chance than of a higher ranked floor. I don't know, but there's lots of things you could put in. So in mathematics, has anybody ever had a hard problem to attack? Yeah, I was going to say, this is just checking to see who's still awake, right? If you're this deep into the program, you've almost surely been given a hard problem. So as you were warned before I began talking, I will occasionally talk about mathematics, but a lot of it is going to be about life advice. When you are given a problem, almost surely don't do the problem that you were asked. Try to do an easier problem first and build intuition.
You would like to say,
Is this the person who's wearing the shirt on from? No. Who wants to say something?
No, you would just say sometimes you should try a harder problem.
Oh, interesting. Yes, because it's like the movie Airplane. Shouldn't we turn on the runway lights now? No, that's what they'd expect us to do. So yes, maybe they're expecting you to try the easier problem, so you should try the harder problem first. Sometimes that actually works. In topology, things are actually easier in higher dimensions than lower dimensions. And so sometimes it is actually better to go the other way. So can somebody give me an easier problem to do?
same thing, but you have infinitely many eggs. You can break as many eggs.
Okay, so if you have infinitely many eggs, then the question is, what does it mean to do in the fewest number of drops? So I don't think going infinitely many is the right way. I think you're off by a minus sign. Yes. So one thing is you could, instead of doing a generic n, you could try to do specific n's. What else could we do to make it easier?
Consider one egg.
Consider one egg. Budget cuts. And unfortunately, this is a school where budget cuts does have a specific meaning. We only have enough money now to buy one egg. And we have to be really careful because that's all we have. So solve the problem with one egg. And maybe once we've solved it with one egg, we can extend to 2 eggs. Do I even have to say what comes next? No, I guess I do. So after 2 eggs, what should we do? 17. You could jump to 17 in this program, yes. Normally people go. So think for a moment, what your strategy, don't say it out loud. What should your strategy be if you have only 1 egg? As soon as it cracks, game over. And you want to find the first floor where it will crack. You don't care how many drops there are. You just need to make sure you find the floor. Well, you care a little bit. You want to do it in the fewest number of drops possible. If it doesn't break on floor 1, you're not going to keep dropping it on floor 1. All right. So what should your strategy be with one egg? Yes.
So on and so forth until it cracks.
There's really nothing else we can do. The proof is very straightforward. If you drop it on floor 2 and it cracks, then it might have cracked on floor 1 and you won't know. So the one egg case is really not that much of a challenge. Yes.
You start on 2 because you know that if it breaks on 2, then you're good on 1.
You don't know that you're good on 1.
Oh, you're right.
It could break on 1.
Okay.
So unfortunately, it could be a really bad building where, and again, this does introduce an interesting question. What is the lowest floor on the building? Is it 0 or is it 1? Since this is a math talk, not a computer science talk, I think it's going to start at floor 1. Does anybody know what floor might not be in the building? 13. Some buildings do not have a floor 13. Okay, so we agree that worst case, it takes order n drops. You drop it on floor 1, floor 2, floor 3, all the way up to floor n. Whenever you do a talk in public, general advice, do not do too much algebra. You will almost surely make a mistake. So right now, I will use the following simplifications occasionally. 1 equals negative 1 equals 0. I will only use that when I'm trying to calculate something up to maybe plus or minus 1. I'm not going to really worry too much about that right now. Okay. So once we have 2 eggs, as soon as 1 egg breaks, we're in the 1 egg case, right? What happens as soon as we're in the 1 egg case? We know what we have to do. We have no freedom. So now, again, think quietly for a moment or two, come up with a strategy. And I don't care if it's a good strategy. Come up with a strategy for 2 eggs. And I'm giving you the hint that once 1 egg cracks, you have reduced yourself to the 1 egg case. So give people just a minute to think. I was so excited. I thought I saw the Fibonacci numbers 1, 1, 2, 3, but then the 4. All right, so can somebody? Yes.
You would drop the first egg halfway up the building, and if it cracks, you
Okay.
would test all the floors below that with the second egg, and if it doesn't crack, you would test all the floors above that.
Good. So 1 is halfway, and if it doesn't crack, wonderful. You've eliminated half the things. I see you. You're in strategic reserve. Okay. You're in strategic reserve. I'm going to call on you in a moment. Okay. So drop it halfway. If it cracks, then you're screwed, and you have to do it 1 at a time. If it doesn't crack, you're going to be in strategic reserve. Okay. If it cracks, you're in trouble and you have to go 1 at a time. If it doesn't crack, you then drop it at 3/4, and it's going to be really good. So what's the worst case if you do the halfway strategy? How many drops? About half. So it's n. Maybe it's n minus 1. It's about n. That's what I meant by negative 1 equals 1 equals 0. I'm not going to wait. Okay. Did you have a different strategy?
Yeah, so like, what if the number of floors is K, then they can.
No, it's n. It's n. K, I know. We're going to use K later for the number of eggs. That's why we can't have the. So there's n floors. Okay, what could we do?
Instead of halfway, we can do like, square root of n,
Okay,
2 root n.
so we can do square root.
And then, essentially, once the egg cracks.
Okay, we're gonna hold off on that. That's a good strategy. I was hoping somebody would say a different strategy than square root. Does anybody have another one? Where I'm saying, I told you were strategic reserve. Do you have a different strategy?
Well, if you're okay with using a couple more, just.
No.
But you would use a couple more in some cases, but you're also free from the dreaded n/2 case where it goes all the way through that.
So where would you drop the first egg?
You can do it at like 1/3 or 1/4.
Okay, so you could do that way. Oh, instead of 1, 3, 5, maybe 2, 4, 6. Good. So the reason I wanted to jump to that and not your answer is a great answer, is that you two give me extreme cases. The first case, if I drop it at n, if it cracks, I'm in trouble, and I've got to do it one at a time. If it doesn't crack, I'm in great shape. For yours, the worst case is that it doesn't crack until the very end. About how many drops is yours going to take? So it's also about n over 2. And again, it could be plus or minus 1, that little bit of difference. So your two strategies are about the same in terms of just how long it's going to take. But then there were some other strategies. Maybe we drop it a quarter of the way, a third of the way. Yes. So you could do something like that as well. And then that would also be another strategy to investigate. Absolutely. Yes. So you can do that, and that's going to be very similar to the square root strategy. So this is one of the reasons why I love coming here. It's tough to do all this in just 51 minutes because you guys see so many great things. What I really want to emphasize right now is, even though we're going to dispose of these, the halfway strategy and the every second strategy are two attempts that have different things for them and against them. What's nice about the halfway is you can eliminate a lot of points, but once you have the egg crack, you have a lot of things potentially to check. The 2, 4, 6, 8, it doesn't eliminate that many, but once it cracks, you're very localized.
I think that the maximum number of things you have to check is the same for both, though.
They're basically the same up to plus or minus 1, and it might even be exactly the same. Given that it's 51 minutes, I don't want to worry too much about that. But it's basically both of them are going to be approximately n halves. And so if we do more generally, we could drop every x floors where x is fixed. And again, there were other strategies about maybe having x exponentially increase. That would be great. Or maybe do a percentage. We can definitely do that. If we do it every x floors, it would be x, 2x, 3x, dot, 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 all the way up to basically n over x times x. I'm not going to worry about is that an integer or not. So worst case, how many drops is that? It's n over x. But then once it breaks, how many more drops is it? Is it x or is it x minus 1? But minus 1 is 0. So we will, and this will be posted with my name online, wonderful, is just n over x plus x. Right? So once it breaks, we have x floors to check, but we've already checked the last one. So there's only x minus 1 left. So what we really want to do is we want to study n over x plus x. And we want to make this small. Does anybody know a technique that allows us to find when this function is small? I'm sorry?
Arithmetic mean geometric inequality.
So we could use that. How do you know that that's going to give you the smallest value?
My teacher told me it gives me the smallest value.
What other technique, what method do we have? Yes. Derivatives, we could use calculus. How many of you have not seen calculus? All right, well, we'll teach you calculus at dinner. Okay, so if you haven't seen calculus, we'll learn calculus at dinner. So if you know calculus, you have a function, check the endpoints, find the critical point. What if you don't know calculus? So we can actually come up with a pretty good idea without knowing calculus. What makes the first term small? How does the first term become small? Yes. When x is big, so we want to make x big, but if we make x big, the second term becomes big. So how do we make the second term small? So we have two competing influences. And so let's be egalitarians and let's set them equal to each other. And if you do that, that gets you x is equal to, or x squared equals n, which then gives you x is equal to the square root of n. So that tells you should drop, and this was suggested, at basically the square root of the number of floors. If you know triangle numbers, you can do a little bit better. I'm probably not going to get to that, maybe, depending on how much time we have. And so we drop at the square root of n. And this balances the two competing influences. Okay. And so is this a proof that that's the best we can do? No. If you do calculus, you can actually do calculus and see that this is the best you can do. And so I'll leave it as an exercise. You can calculate to the function n over x plus x. But we've definitely shown that we're at least at the right order of magnitude. Because if x is of size square root of n, then the second factor is of size square root of n, and this is of size square root of n. If x is larger than square root of n, then the total amount is going to be greater than square root of n. If x is smaller than square root of n, the first factor is going to be less than square root of n. So we know we can't do better than something of size square root of n. So even if I don't know that this is the best, I know it's approximately the best. I know I really can't do much better than some constant times square root of n with this method. So we talked about how to do this. Oh, lovely. So sometimes when I display things, it doesn't keep things as superscripts. So if we set the two terms equal to each other, we get x equals the square root of n. So the number of drops we would have when x equals the square root of n would be n over square root of n plus square root of n would be basically twice the square root of n. So that's how many drops it would take. This is a plot when we have 100 floors of 100 over x plus x. What does the minimum look like? 10. Is that a proof? No. So what we can do is we can look at n over x plus x, and here's a good idea in mathematics: change variables. We just saw from our heuristic that it looks like square root of n is that critical threshold for how many floors we should drop it at. So if we let x equal t square roots of n, then we have n over t squared of n plus t squared of n. We can pull out the square root of n now, and we just get right, so some of it is missing, but I can redraw a t. The square root of n, 1 over t plus t. What's nice now is there's no n dependence in 1 over t plus t. And we can just ask, what is the smallest possible value 1 over t plus t can take on? And again, as arithmetic mean, geometric mean was mentioned, that's a great way to look at this and see that the smallest value can take on is 2. But again, what's nice about this is we've pulled out the n dependence, and now we have something here that's clearly going to just be a constant. So we can't do better than something on the order of square root of n. Okay, as I said, you can use calculus, and I guess this exponent should go up. It's somehow been destroyed as it's projecting. Okay. So imagine I have two algorithms, and let's see, you had volunteered your life before. You want to volunteer again? Or no? Okay. So one algorithm always takes 1,000 seconds. You know what you're getting with it. 1,000 seconds. The other algorithm takes 1 second almost always, except basically once in a million inputs. It's going to take 1 billion seconds. On average, they both take approximately 1,000 seconds. Which algorithm would you like to use? Yes.
Something, man, because if you notice it's taking 1 billion seconds, you can stop it.
Good. So you're saying, I don't want to answer your question. I want to answer a better question. I don't want to use either algorithm exclusively. Yes.
I mean, yeah, you could either use both at the same time, or you could probably just, a lot of the times, I mean, the algorithm works in 1 second. Depending on the situation, it might be much more valuable. Like, let's say if you're like doing stock trading, right? And the faster you get like a answer,
right,
the better.
Yes.
And the 1 second might be more beneficial because if you're 1,000 seconds, you're too late.
Well,
it doesn't matter when you're too late.
The real thing is, are you able to stop and switch algorithms?
So 1 billion seconds is 30 years. It is a little concerned.
So, but again, we were willing to bet with his life. You've got 30 years to spare. You're young. I mean, I don't know if I have 30 years to spare. I'm in my 50s. So good question. So let's say we're going to be doing this maybe 1,000 times. And again, even with 1,000 times, I'm not really that worried that this is going to happen once in a million. Well, if I do it 1,000 times now, it's unlikely, but it's not so unlikely that I would be surprised. And so as long as you have the ability to switch algorithms, what you do is start with algorithm 2. If it takes more than a second, you know you're in the bad case, and then switch to algorithm 1, which will run in 1,000 seconds. So you don't have to stay with one approach the whole time. You can start with something and you can be dynamic and you can adjust. And so what we really have is we have two egg strategies that are extreme. One of them, when we drop it halfway, is really good if it doesn't crack. It eliminates a lot of things on the first one, but once it cracks, bless you, we are stuck going through a lot of cases. The other one is much better in that once it cracks, we've basically localized to within one where it is, but it could take us a long time to localize. And so we want to try to find a way to balance the two different approaches. There is the triangular stuff that people have mentioned. Instead of dropping it the same number of floors every time, you drop the most after the first one. And if it doesn't crack, then you drop one less, and then one less, and then one less. And the reason is because every time you've dropped it and it hasn't cracked, you've already added one more drop. So you want to have that first drop a little bit larger. This is similar to the ideas people were having about doing some type of proportion, is do a little bit bigger at some point. Okay, so I'm not going to go into the details of that, but the people who've mentioned triangle numbers, that's exactly what you would want to do. If you have 105 floors, you don't do the square root of 105, but you would do 14 for the first, 13 for the second, 12 for the next. And now, whatever floor it breaks on, if it breaks on 12, I have 11 more things to do, but it took me 1, 2, 3 drops to there. So 3 plus 11 would be 14. If it breaks on the 14, it's 13 more drops, and 1 to get there. 1 plus 13 is 14. Now it's the same number of drops no matter which floor it was. Whereas in the others, depending on where it is, it could take a little bit more than the other. But they're all about the same order of magnitude. All right. As no one is surprised, we could imagine we have 3 eggs, or more generally, K eggs. So think for a moment about what would your strategy be with 3 eggs. So just think for a moment. I'm going to give everybody a chance. So what do we do with 3 eggs? And that's about the limit I was willing to spend in terms of my budget. They didn't have the 6-pack, so I only have 3 eggs on me. Which means I do have an opening for another kid in my family because I've got 3 eggs now. So does anybody have a strategy for 3 eggs? Somebody who hasn't spoken, maybe. I think that's the heavens, yes.
Yes, you could use the same strategy as a similar strategy as before. Where you drop it from halfway, and then if it cracks, then you drop it from halfway between the first.
Okay, so one is to take the halfway strategy, and that's an absolutely good thing to try. But we knew that there was something better than the halfway strategy. Yes.
The same strategy and do root n for the first egg, and then
So why root n? So one of the things you want to learn in life is to love free parameters.
Okay.
Free parameters are wonderful because right now you're committing yourself to square root. Are you absolutely sure? Are you willing to bet your neighbor's life? Either one. Or you could even be the people in front of you. We could do like all 4 or 5 of them, right? Anybody here ever see Legally Blonde? Where they go, are you willing to bet your client's life? No. So instead of doing square root of n, what should we do?
Every K.
Right, but we don't know what it is. We'll figure it out later. We do it every x. So we do it every x. Worst case, it takes n over x. From this point onward, what happens? Yes.
The range within which it cracks, and then you use your next egg and do some x like y.
Good. So what problem is it now? It's now the 2 egg problem. But I'm going to ding you a little bit because I can. It's not the 2 egg problem. You have to give me a little bit more information. It's 2 eggs with x floors, right? So it's not just the 2 egg problem. It's the 2 egg problem with a specific number of floors. And we just showed, and this is one of the reasons why I like to do it like this and not on. So it takes about 2 times the square root of the number of floors drops in the 2 egg problem. That's what we showed. Okay. So now, when we're doing this, it's going to be 2 times the square root of the number of floors, which is x. Okay. How can we find the smallest value of this? Calculus, right? Things haven't really changed that much. Is this problem significantly harder to use calculus? No. Right? But this is supposed to be a calculus-free environment, range-free eggs, all that. I thought that was reasonable. All right. So how could we do this without calculus? How could we get a feel for what the answer should be? You could use that. What else could we do there? Yes. Yeah. So if we set n over x equal to 2x to the 1/2, then we would get n equals 2x to the 3/2. So x is equal to n to the 2/3, and I'll call it C3, where that's just some constant. I'm sorry? That's why we have the constant C3. So there is a computable constant there. It's probably going to be 1/2 over here, take the 2/3 root of 1/2. Yeah. But that matters a little bit. But what I really care about is I care about the n dependence. If you think about what's going on, if x is of size n to the 1/3, then this would be of size n to the 2/3. This would be n to the 1/6. This term would be a lot larger than that. So taking x to be 1/3 is not good. If I take x to be square root of n, this term would be of size square root of n. This term would be of size n to the 1/4. Not good. But if I take x to be of size n to the 2/3, the first term is of size n to the 1/3. The second term is of size n to the 1/3. And so that looks like a good choice. So we would say x should be on the order of n to the 2/3, and the number of drops is about what? How many drops would it be? Give me the dependence on n. I don't care about the constant. We'll call it C3 tilde. N to the 1/3. Well, I'm combining the two terms, and I'll just call that some new constant. So all I care about is the constant dependence. So if I take x to be of size n to the 2/3, each term is going to be of size n to the 1/3. Okay, so if we do 3 eggs, we know what's going on. So let's summarize our knowledge. So number of eggs, floors for dropping, the number of drops total. When we had 1 egg, how many floors did we have to drop? Every one, and the number of drops total was n. With 2 eggs, how many floors for dropping? Square root of n. And how many drops total? And I mean, I'm giving you 3 data points. That's really generous of me. With 3 data points, with 3 eggs, how many floors for dropping? N to the 2/3. And there might have been a constant here. I don't care. And how many drops total? Does anybody want to rewrite any of the numbers in the table to be more illuminating? Yes.
I think it's 2 times n to the 1.
I don't care about constants. As long as I have the exponents correct, I don't care about constants. Yes.
1 is n to the 0.
1 is n to the 0, almost. Not n to the 0. You're close. Yes. N to the 0 over 1. You were so close. You forgot to divide by 1. I'm actually going to take off points for not dividing by 1.
And n is n to the 1.
1 over 1. You just don't like dividing by 1, okay? It's really not that bad. I'll show you over dinner how to divide by 1 really easily. Do you know how to multiply by 1?
He's shaky on it.
Oh. Years ago, the Williams Record had an article where they asked a bunch of math professors what were their favorite constants and why. And with the straight face, I said the golden mean, because among its many remarkable properties, it's the reciprocal of its own inverse. And they printed this. Yeah, if you can say things with a straight face, it's amazing what you can get away with. So do people detect a pattern here? Can you figure out what to do for 4 eggs? So you can prove by induction without too much trouble that you could at least do this well. Okay. So I just want to make sure, what time am I supposed to stop at? 5:34. Okay, so I've got plenty of time. Wait, 5:34, that's an hour.
Yeah.
Oh, that was only 51 minutes. I have an hour. Okay, so we have plenty of time then. Okay. So everybody is comfortable with proofs by induction? So I will assume that everybody has now done a proof by induction that these formulas are correct and they generalize. So we should have enough space to squeeze it in. If we have K egg, it's going to be some constant n to the k minus 1 over k and some constant n to the 1 over k. And everybody has proved that by induction. Does this mean we've proven that this is the best you can do? No, we've just proved with this method, you can do this. So I have done some research with students on generalizing this problem. And so there's a lot of ways you can generalize this. And so one of the things we did is imagine that we had a building where there was both a horizontal and a vertical component of how it would break. And depending on how you want to choose things, what's the minimum ways you can do it? I want to talk about another way you could do this. So if we have 4 eggs, which was beyond my budget, I only have 3 eggs on me, I'm sorry. So how would you do the 4 eggs? What do we do? Okay, so basically, drop at constant times n to the 3/4. Break. And then the 3 egg problem. Okay. Do you all agree on this? Is there any other way we could do it? Is there any other way to approach this problem?
Well, I mean, I think this is kind of how you get the numbers, but the idea is you want your previous method. So when you're on 4x, you want each new egg drop to get rid of the amount that your previous method would take up, essentially.
Okay.
I don't know what it is exactly before, but I know for 3 it's the
Okay, but you're still going to be roughly the same. You might get a little bit better constant, which could be important. And again, trying to find the best constant is important. Is there another method we could approach? So basically, as soon as 1 egg cracks, we're down to the 2 egg problem. So I do have another approach. I don't know if it's better or worse. So let's do a digression. So almost everybody knows calculus. All right, so quick crash course in calculus, okay? So we have a function f of x. We associate the derivative f prime of x. The name is really good because its name involves f. It's derived from that. We define it as the limit as h goes to 0 of f of x plus h minus f of x over x plus h minus x. Of course, you can rewrite x plus h minus x as just h. What's really going on is if I have a function and I want to find its derivative at some point, what I'm doing is I'm looking at points very close by, and I'm looking at the change in y over the change in x. That's the instantaneous, that's the average speed over a small amount of time. I'm letting the interval get smaller and smaller and smaller. And as that gets smaller and smaller and smaller, the average speed converges to the instantaneous speed as long as things are nice. You can prove a lot of things in calculus formally, or you can do some quick informal arguments. If you are on a train in the classical world, in case there's any physicists here, and the train is going at 100 miles an hour, and you're running on the train at 6 miles an hour in the same direction as the train, how fast does somebody on the ground see you moving? 106. Speed is additive. Are there any physicists in the audience? My apologies. Okay. Speed is not additive. Some of the students here know I actually, at least one student here knows I jog or run sometimes. I do not run at nearly a fast enough speed for relativistic effects to matter.
Are you sure about that?
I am very sure about that. I have seen what my top speeds are. We actually have, I mean, we don't really have that much to do. Oh, this is being recorded. We have a lot of fun things to do in my hometown. It's sometimes really difficult to choose what to do on a Saturday night. There are places near the schools where they actually have signs that tell you how fast cars are going. And if you jog or run very quickly by them, you can actually get your instantaneous speed. And so I have seen what I'm able to top out, and it is nowhere near anything relativistic. In the classical world, speed is additive. This is a great example of how easy it is to be misled by everyday experience if you are suitably restricted. Every now and then you read something that sticks with you. My high school physics book had the following quote or paragraph on special relativity. This was one of Einstein's brilliant theories that speed is not additive, that nothing goes faster than the speed of light. And so if you have two things that are traveling really fast, their speed is not the sum, but it's a little bit decreased. And so these results might seem counterintuitive to most people, but you have to remember most people don't have experience traveling at 3/4 the speed of light. I'll let that sink in. Most people don't have, I don't know anybody who has experience traveling at speeds anywhere near 3/4 the speed of light. When you're traveling that fast, things look strange. So here's a wonderful fact about derivatives. If I give you f1 of x, and I give you f2 of x, and I ask for the derivative, what is the derivative of the sum? The sum of the derivatives. Okay. How many of you have seen a proof of this in calculus? And they do a whole limit argument, correct? They would say, let's let a of x be f1 of x plus f2 of x. Then we look at the limit as h goes to 0, a of x plus h minus a of x over h. And you use your limit laws, you group everything together, and you get the derivative of a sum is the sum of the derivatives. Do you ever prove anything beyond that? Yes.
Argue and
Okay, but anything else involving sums?
I mean, the difference between.
Okay. Sure, I mean, sum and difference are very similar. Anything else about sums? We did the sum of two terms. Yeah.
Some of it.
The sum of n terms. Do they actually prove that? No. How would you prove? You could, yes. So you could use induction. And so this is grouping. So if you have f1 of x plus blah, 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 plus fn minus 1 of x plus fn of x, I can group all of these together. I can group it like that. And now I have a sum of two terms. And now I can use my result that the derivative of a sum of two terms is the sum of the two derivatives. And so if I take the derivative, I don't know why I changed color and not changing screens. So if I take the derivative of this, then it would equal f1 of x plus dot 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 plus fn minus 1 of x plus fn prime of x. And now you just continue by induction. By induction, you know that the derivative of that is the sum of the derivatives. So do we know that the sum of any number of functions, the derivative of that sum is the sum of the derivatives?
Finite.
Finite. So we do not know for infinite. So if I give you f of x is the sum, and it goes from 0 to infinity, if I can do this correctly. Let's do sine 4 to the nx over 2. How many of you have seen series like this? Does that sum converge? Yeah. How large can the numerator be in absolute value? 1. So the numerator converges. The numerator is bounded. It's between -1 and 1. The denominators are going very rapidly. This converges. Each individual summand is differentiable, but this function is actually not differentiable. I'm going there because I'm seeing some things on the blackboard, and one of my rules is, at all possible, you try to work in what you see into your talk. And you can ask about the space of functions that are differentiable, at least at one point. And it's really interesting questions talking about how big is the space of functions. It turns out I can give you a function that is differentiable nowhere. And so there's a lot of fun stuff related to problems like this. Here's an infinite sum. The derivative of an infinite sum is not necessarily the infinite sum of the derivatives. I have to be very careful when I do things by induction. I only know that in the case of a finite sum. And the reason I'm bringing this up is I love this idea of grouping, putting parentheses and grouping things together. So I'm going to try to use beautiful colors. All right. Those look like 4 golden eggs. Thank you. I like the, sure. Yeah, it's getting close to dinner. If we say yes, maybe we can eat real eggs. Okay. So, oops, I don't want to do that anymore. I want to switch to this. So here is my first egg, and then the 3-egg problem. Right? Can somebody give me another way I could break these eggs up? Yeah. What if I broke them up, 2, and then a 2-egg problem? So what I do is I basically amalgamate a bunch of floors. And so I have, 1, 2, ... f. F plus 1, ... 2f, ... This now becomes my superfloor 1. This becomes my superfloor 2. And so I do the 2-egg problem on this like superfloor construction. So I've never done this part of the talk before. So I was working on this on my jog this morning. So but I was not really thinking too much about this, just enough to see that it would be interesting. So if I do these superfloors, what I can do is I can do the standard 2-egg problem to find which block from f of length big F is it going to be. Okay. So if I have n floors, I do it in blocks of size f. How many floors do I have for the initial 2-egg problem? So how many floors do I have for the initial 2-egg problem?
Oh, n over f.
I have n over f.
That's number 4.
So I have n over f floors for the initial problem. Okay. And then once it breaks, how many more floors do I have? F. So how do I choose F? I have the 2-egg problem for n over f floors. Then we have a 2-egg problem for f floors. Yes.
You probably want to, for each one, use the formula we know for the 2-egg problem.
Okay.
Calculate like best value of f.
So what can I do for n over f? What's the best I can do for that one?
2 root n over f.
2 root n over f. So I'm going to do it as 2n/f to the 1/2, right? That's the best I can do from the first 2-egg problem. Does everybody agree that that's the best I can do from the first 2-egg problem? I have n/f floors, and so we know the best we can do is 2 square root of n/f. Now I have to add the 2-egg problem applied to f floors. What's that? 2f to the 1/2. So I want to minimize this. Okay, I want to minimize exclude constants. Okay, I'm going to exclude the constants, okay? That's bad, but it's n to the 1/2 over f to the 1/2 plus f to the 1/2. What does that tell me? What should f do? What should f be? N to the 1/4. So what we should get is if we have n to the 1/2 over f to the 1/2 equals f to the 1/2, that implies f equals n to the 1/2. But did I do it wrong? Oh, so the floor is f is f is n to the 1/2, right? Yeah, I just wrote the wrong thing. Yes. So f is n to the 1/2. And so then that means I have the total cost is going to be n to the 1/2 over n to the 1/4, right? Because I have f to the 1/2. If f is n to the 1/2, the square root of f is going to be n to the 1/4. Plus f to the 1/2, which is going to be n to the 1/4. This is order n to the 1/4. What else was order n to the 1/4? The 1 and 3. So my question to you is, do we actually gain anything by doing it as two-egg problems versus doing it as a 1-egg problem followed by a 3-egg problem? It depends what the coefficients are. And now all of a sudden it matters. And so now all of a sudden, how we do the grouping matters. I could put people on the spot and say, how many of you think it doesn't matter? How many think it's better one way? How many of you think it's better the other way? I'm not going to, but I could. It's at least worth knowing that these are things worth considering. That there's often more than one way you could attack something. It's very easy to fall into a local maximum, into a local maximum or local minimum rather than a global maximum, global minimum. I'm going to do one of my favorite problems. I've actually met the dog that's involved in this. I am a terrible artist. This is a dog. Okay. It has to be dog because it's labeled dog. Okay. If I throw the stick in the water, what path is the dog going to take to get to the stick? Yes. If you've seen the problem before, don't speak. If you haven't seen it before, you can speak. Okay, so if you've seen it, if you've
I just have a question.
Yes.
Does the dog move slower or faster in the water?
Good question. Dog moves faster on land. What path should the dog take to the stick?
In this case, the dog starts in the water, so a straight line.
Straight line. And what if I throw the stick very, very far away? Yes?
Get out of the water.
Get out of the water. Do you run straight down or do you run at an angle? Or swim at an angle?
Well, it depends, because if you run at an angle, like you need to spend time in the water, but because of like Pythagorean theorem, it's shorter.
Right. We'll assume no current, which is a good question. So the dog actually travels at an angle like this. If the dog traveled infinitely fast on land, this is super crypto, then the dog would go straight down, run along land, and then go straight back up. So if the stick is sufficiently far away, it's actually worth taking a hit in the beginning to get onto land. If you ask at every moment in time, what should the dog do to get to the stick as fast as possible? So this is the greedy algorithm. This is doing at every moment in time what is best. Does anybody live their life by doing what is best for you at that exact moment in time? Almost surely not, right? There are plenty of unpleasant things that you do because you know long-term it's going to help you for doing them. But at the moment, it's probably not the most pleasurable thing you can do. Not everything is, hearing a math talk at, Hampshire College, right? So if you want to know locally what's the best thing the dog can do, the best thing the dog can do locally is go straight for the stick. Globally, if the stick is very far away, it's worth going on land. So there's a wonderful series of papers. Tim Pennings is the guy's name, and the dog's name is Elvis. And he's actually done the experiments. I've met the dog where the dog knows to swim at an angle that's approximately what it should be. The papers are, do dogs know calculus? And do dogs know bifurcations? It's interesting that he doesn't ask, do my students know calculus? We'll not comment on that too much, but you can actually use this to prove an inequality that was mentioned earlier today, at least twice. What inequality? AM/GM can be proved by this. And you look for that critical distance where the dog is now indifferent between swimming straight for the stick and going on to land. And so, in the paper, do dogs know bifurcations? He actually uses this to prove the arithmetic mean, geometric mean. So if anybody's interested in trying to pursue stuff like this further, I would love for somebody to work with me on seeing, is there a difference in 1 egg, 3 egg versus 2 egg, 2 egg? We know that they have the same order of magnitude. They're both going to be on the order of n to the 1/4 for the number of drops. But is there a better constant term in the simple methods for the two of them? So if anybody's interested, please let me know. My email address is sjm1@williams.edu. And then my students and I will be here over dinner. We're happy to talk about this. We're happy to talk about what is it like to go to different types of colleges. I'll stop recording right now so they can say just where they are from.